Hello, everybody. I'm William from UIUC. Today, I am excited to present my work on DChannel, accelerating mobile applications with parallel high latencies, high bandwidth, and low latency channels. And this is a joint work with my advisor, Brighten Godfrey, and also so many great collaborators from different institutions. Okay, so low latency is very critical for many applications. In fact, one of the most widely used mobile applications, which is the web browsings, is significantly affected by latencies. And it is also true for many interactive applications, mobile applications that utilize many API calls to the cloud services. And low latency is even more important for emerging applications, such as the virtual reality and cloud gaming, where the latency determines whether your experience will be usable or not. For example, VR requires less than 20 milliseconds of latency, while the cloud gaming requires even less. So what does the current 5G latency look like? To find out, I went to Chicago and drove around in the downtown area, and I tried to measure the packet round-trip time over the time. And I plot the graph here in the time series graph, while the y-axis shows the packet round-trip time. As you can see here that the latencies is very variable. It can give you 18 milliseconds in the minimum, but it spikes to 300 milliseconds in the maximum. So if we plot that kind of like 5G that you have right now, which is the 5G eMBB, 5G called it as the enhanced mobile broadband, in the latency and throughput graph, this is where 5G eMBB sits. It supports high throughput, like up to 2 Gbps end-to-end throughput, but it also come with the high and inconsistent latencies. And this 5G is actually what your mobile phone is using right now on your device. It supports general mobile applications, basically. And it will also support like lots of high bandwidth applications, such as the video streaming on 8K. However, 5G also gives you a different channel, specifically for achieving a consistent low latencies, called the URLLC. This channel sacrifices the bandwidth to get a consistent low latencies. Specifically, URLLC is designed to support mission-critical applications that require very low latencies, but also have a very low bandwidth requirement, such as the remote surgery or factory automation. But there are so many applications that sits in the region where it requires low latencies, but requires at least a moderate amount of bandwidth. How can we support those? In order to answer these questions, I want to answer these questions first, which is like a very hard questions. Can we actually break the latency and throughput trade-off? And we are trying to see it from a different perspective. Instead of trying to design a single physical layer that have both high bandwidth and latency, we try to solve the challenge in the higher level by using both channels, eMBB and URLLC, in parallel so that we can get the best of their properties. Well, to keep you excited, let's see how much improvement that this approach can give for web browsing, which is the most widely used mobile applications. The yellow bar here shows the web page load time if we use only eMBB, which matches how web traffic is currently delivered. And if we use URLLC only, it performs worse compared to the eMBB only, which is unsurprising because URLLC bandwidth is very limited, and the limited bandwidth becomes the major bottleneck. However, if we decide to combine those channels carefully, we can do much better than either channel alone, with 20 to 40% faster page load time, which is actually surprising given that the URLLC bandwidth is only less than 1% of the eMBB. So why using URLLC in addition to eMBB can help? Let's take a look at the typical traffic for the web browsing. To load content, client phone needs to do the DNS request with the DNS server. Then it needs to do the connections handshakes on TCP and also an SSL TLS handshakes. And finally, the client will request to fetch an object, and the server will deliver the objects. And actually, most of the traffic, such as the handshakes itself, are tiny. And the delay comes from the network latencies and not the limited bandwidth. If we can use URLLC carefully, we can deliver this traffic to URLLC and get a significant speed up, which explains our result when using both channels. So how we are going to use the eMBB and URLLC? To use both, we introduced DChannel. DChannel connects to URLLC and eMBB and provides a single virtual channel to the application so that it can give both high bandwidth and low latency to the application. DChannel works by steering IP packets in the network layer, and we don't require any link or physical layer modifications on 5G. And also, DChannel can steer traffic transparently and don't require any application input, so you don't need to modify your application. This is the overview of the DChannel architectures in 5G. There are two main components of DChannel, which is the DChannel client and the DChannel proxy. The DChannel client sits in the mobile phone, and the DChannel proxy sits in the packet core gateway in 5G. The DChannel client and proxy are connected with eMBB and URLLC, which spans across the base stations and the core network. Okay, so first, the DChannel client captures packets incoming from the client and implements an algorithm to steer the traffic between those two channels. On the packet core gateway, DChannel proxy reorder packets and finally deliver it to the server application in order manner. And the same actually goes from the incoming traffic from the server to the internet, from the internet to the client application. Well, next I'm going to discuss about the DChannel design decisions, which actually within this kind of like two ideas, two kind of like key points. The first one is the granularity of the traffic steering. The second one is the steering heuristics. The first question is about the granularity. Given that we have two channels, in which granularity we should steer the traffic? Well, the first approach is to steer traffic in the application level, which translates to steering web objects in the context of web browsing. And here, the traffic steering should determine whether it should fetch object by performing an HTTP request on eMBB or URLLC socket. And the reasonable solutions for this is, of course, to only fetch small objects on URLLC, because URLLC is very bandwidth limited, and we fetch large objects on eMBB. However, there are some problems on this. First, we miss opportunity to accelerate the latency-sensitive operation within the HTTP request itself, which is DNS, TCP connections, HTTP request X, and etc. The second, it also requires application-level information, and we want to avoid that because we don't want to modify the applications. This means that we should steer traffic in the finer granularity, which is steering in the network layer. So the second option is the network layer, which is steers based on the IP packets. Given that we have a packet, PN, where should we send it? To URLLC or to eMBB? And because splitting packets between URLLC and eMBB can cause out of order, we introduce the reordering buffer. And we choose to add this because most applications, typically applications that use TCP, don't like out of order and will instead wait for all previous packets to arrive. And the key idea of using URLLC efficiently is to treat it as expensive resources, so that we only offload small portions of the traffic to the low latency channel. However, it should also give you most benefit, so that we come with a solution, which is the cost-reward analysis to simplify our problem. So that we only send a packet PN to the URLLC if we see that its rewards will outweigh the cost. The next question is, how do we define rewards and costs? So the rewards is defined with the simple kind of questions. If we use URLLC, how much faster will a packet be delivered? And for the cost, how much will the URLLC utilization increase if we use URLLC to deliver that packet? To give you a better idea about the rewards and costs, I give you these simple illustrations. We have a sender timeline on the left and also the receiver timestamp on the right side, and we want to decide whether this packet, PN, should be delivered over URLLC or eMBB. Well, first, we need to estimate the delivery time of the channels. So we are using a formula of the additions of one-way delay of the network path, URLLC or eMBB, and also the queue depth, queuing delay, and also the transmission delay, which is packet size divided by the bandwidth. In this case, if we send the PN to the URLLC, then this will be the arrival time of the packet, but the URLLC utilizations will increase. If we decide to send it on the eMBB, then the packet will later arrive because it has a high bandwidth. And this is the arrival time of PN if we send it to eMBB. And this is how we calculate the rewards, which is basically how much faster this thus the arrival time will be if we decide to send it to the URLLC. Now the question is, because URLLC channels is so fast, if the channel is not congested, then we should expect to have a rewards, like on most of the case. Should we always send the packet to the URLLC if we expect a reward, if the reward is not negative? Let's see another kind of use case for this. So this is the same. We still want to send a PN, whether should send it to eMBB or URLLC, but we have a previous packet, which is like the PN-1. The PN-1, we already sent it to the eMBB. So PN-1 will arrive roughly in this timestamp. If we decide to send PN, the next packet, to the URLLC, then PN will arrive at the receiver at this timestamp. However, we need to queue up the PN so that the arrival time actually becomes the arrival time of the PN-1 because we have a reordering buffer. And the second is because applications typically will wait for the previous packets to arrive before you process that particular packet. And if we decide to send this PN to the eMBB, then the arrival time will be roughly in this time. Then in this case, the read is actually, you can still see a rewards, but the rewards is practically very small and close to 0. The question is, should we still send PN to the URLLC? Well, this is where we introduce the cost, which tied to the current URLLC utilization, which I represent as the QDAP, the current QDAP at time t, and also the packet size. How much bigger is actually the packet that we want to send? And we divide it by the bandwidth, and we calculate it as a cost. So we decide to only send URLLC if the rewards is better than alpha time the cost. I introduced this alpha parameter as the balance between the rewards and costs, which translate to how much cost that you want to pay in order to get a certain bandwidth. For example, if alpha is 0, then you are going to be expecting to send a packet every time you see a rewards. And in this case, let's revisit this case. Should we send it to PN to the URLLC or not? The answer is might be not, because the rewards will be very small, and you will be seeing the packet on the, we will be increasing the cost on the current utilizations of the URLLC. There are lots of details on the paper, such as how do we pick a good alpha. We decide to choose 0.75 based on the experiments that we did. We detailed it better in the paper. And how do we estimate the network latency and the QDAP, how the performance and the wrong latency estimate, and also the details on the reordering buffer. So there are two implications of the cost reward heuristics. The first one is small packets and short packet sequences tend to be steered towards the URLLC because the rewards will be high, and also the cost is also low. And long packet sequences tend to be steered towards eMBB. This is because delivering them to URLLC will significantly increase the cost because of the increased QDAP. And also when the queues build up, the eMBB can deliver this faster. And the implications of this steering policy is, this implications actually suits well with the idea of accelerating only control packets, such as TCP SYN and ACK on the HTTP-based traffic, and small messages, such as HTTP requests. So in the evaluation, this is the main question that we want to answer. How does combining both channels improve the application performance compared to the eMBB only? And I tested existing schemes on MPTCP. The first one is MPTCP, which already combined those two paths on the transport level. And I used the default one. And for the ASAP, this is designed for steering traffic in two different paths. The first one is the satellite network, and the second one is the 4G network. And those combinations have the similar bandwidth and latency trade-off. I tested 3 types of applications, web browsing, on HTTP2, and also web-based mobile application, including Reddit, eBay, and bulk download. We did the experiment in both emulated and live 5G eMBB because the URLLC is not deployed yet. We can only emulate URLLC. And for the eMBB, we record the network traces in the downtown Chicago that represent a metropolitan area with 5G millimeter wave, and also our campus UIUC that represent a rural area with 5G low-band deployment. We record the traces in 3 different conditions: a stationary, low movement, walking, and moderate movement, which is like driving. And for the live network, we also did it in Chicago and our campus, but we only tested the stationary conditions. We sent this traffic through a tethered 5G phone. Okay, so this is a figure that shows page load time improvement compared to delivering the traffic only to eMBB, which is how the web browsing traffic is currently delivered. The x-axis shows the different traces used, and the y-axis shows the percentage improvement. Overall, DChannel improved web browsing by 20 to 40% compared to the eMBB only. Next is MPTCP. Well, MPTCP does not perform well in this URLLC and eMBB pairs, because MPTCP is well known to work good only under multipaths that have similar latency and bandwidth. And we know that the URLLC bandwidth is a rounding error compared to the eMBB. And the next is a related work called as a ASAP. ASAP accelerates connections, handshakes, and HTTP request traffic to the low latency path, which is URLLC in this case, but leaves the HTTP response because it is typically big to the high bandwidth path. And based on the result that we got, DChannel managed to beat ASAP in every conditions because DChannel has a finer traffic steering granularity compared to ASAP that only steer in the kind of like HTTP phase. And also ASAP is bound towards the HTTP traffic. So the result that we just saw was for web page load time, which includes a mix of objects and non-network related delays, such as like processing delay and rendering delay. We can get some clarity on where the improvement comes from the Microbenchmark, which is transferring individual objects based on the specific size. So for small objects, we see most benefit because DChannel will most likely send all traffic to the URLLC because the traffic is small. And this is similar to the improvement that we get if we only use URLLC. However, moderate size objects cannot be using URLLC because will be too big and then the bottleneck will shift to the bandwidth. But DChannel still get a big benefit by accelerating control packets traffic, like connection establishment. One thing that surprises us actually is we also see the DChannel improvement in bulk download by about 10%, even though URLLC technically only give us less than 1% of the bandwidth of eMBB. So what happened here? Well, we did the experiments using the emulated mobile driving traces, where the bandwidth is very variable. And DChannel steering policy chooses to accelerate TCPX, which makes the TCP control loop faster so that it can react to the changes of the bandwidth faster, resulting in a higher average throughput. There are more evaluation results in the paper, such as we evaluate in the live 5G and confirms our performance gain. And also, DChannel lowers mobile application response time by around 21%. We also evaluate reordering buffer that it actually helps DChannel. DChannel also gives improvement even when URLLC bandwidth fluctuates, and DChannel still works with an incorrect latency estimates. There is one main key takeaway that I want you to get, even though you don't kind of like remember all the details of my talk, which is using URLLC and eMBB can give illusions of having a single channel that is both high bandwidth and low latencies. And for future directions, we plan to support specialized applications that requires both high bandwidth and low latency in mobile environment, such as the extended reality, VR/AR, cloud gaming, and remote driving. Thank you.